Welcome back, students. In the last class, we were talking about the drawbacks of Bohr's model, and in that, we did de Broglie's concept. So, today we'll continue with the same topic and we'll be doing the next drawback. And the next setback, which came for Bohr's model, was actually the Heisenberg's uncertainty principle. So, it is Heisenberg's uncertainty principle. Well, Heisenberg uncertainty principle, it also became a drawback of Bohr's model because Bohr's, in his model, could predict the velocity of electron, which are moving in different shells. So Bohr gave us an idea that the electrons which are closer to the nucleus experience higher force of attraction from the nucleus, so they move with a higher velocity so that they'll not fall into the nucleus. So that they'll generate sufficient angular momentum which will counterbalance the force of attraction from the nucleus and the electron will not fall into the nucleus. As we move away from the nucleus, the force of attraction decreases, so the velocity of electrons in the shell also decreases. Heisenberg gave it a serious dent to this concept. He gave a concept according to which we cannot predict the velocity and position of an electron accurately at the same time. Let's see what this concept is. Well, suppose this is the nucleus I have got, and this is the shell in which electron I have got. Now, according to Heisenberg uncertainty principle, it is simultaneously and precisely impossible to determine both the position as well as the velocity of an electron in an atom. That means, as far this electron is concerned, you cannot predict its velocity and its position at the same time. Suppose you are predicting the velocity with the accuracy, there will be some uncertainty in the position. Well, as far electron is concerned, here I'll explain it to you in a different way. Suppose here you have got a detector for this electron, and somewhere here you have got a light source. That light source or that radiation source will radiate energy, and that energy will fall into the nucleus, and that will make this fall into the electron, and that will make this electron visible. Now, suppose I am using a light of larger wavelength. There's every chance that this light will not strike on the electron. So I will not get its position accurately. Although the velocity of the electron will not change, but I will not get the position of the electron accurately. The second method I have got is that I can use a radiation of smaller wavelength. Now suppose I am using a radiation of a smaller wavelength, and this radiation strikes on the electron, and I can easily locate where the electron is. But you know, I've taught you already that energy of radiation is equal to h into c by lambda. So when lambda is smaller, the energy of the radiation is higher. So when radiation of such a high energy is striking on the electron will get accelerated, its velocity will change. So in the first instance, when I was using light of a larger wavelength, what was happening? The velocity of the electron was not changing, it was accurate, but I could not calculate its position accurately. In the second instance, when I can calculate its position accurately, the velocity has changed. That means it is simultaneously, if you want to write it down, you can write it down. This is the Heisenberg's uncertainty principle, that it is simultaneously and precisely impossible to determine both the position as well as the velocity of an electron in an atom. What Heisenberg did, he related these two uncertainties with the Planck's constant. So according to him, if delta x is the uncertainty in position and delta v is the uncertainty in momentum, then according to Heisenberg's uncertainty principle, delta x into m into delta v is greater or equal to h by 4 pi. I'm writing it here again. It is delta x into m delta v is greater or equal to h upon 4 pi. Well, my dear students, we generally write it like this, but whenever you have to do numerical based on this, you'll not use this greater than, you'll use only equal to h upon 4 pi, where h is the Planck's constant. So delta x is the uncertainty in the position, delta v is the uncertainty in the velocity, and m is the mass. You know one thing, that if velocity is changing, definitely the momentum is going to change. So what I can say, delta x, that is uncertainty in position, into delta p is greater or equal to h upon 4 pi, where delta p is the uncertainty in momentum. So again, this concept, it made a serious objections to Bohr's model, and according to this concept, it was not possible, like Bohr was predicting the velocity of electrons in the first shell, second shell, third shell. According to this concept, you cannot predict these velocities, but because what you are doing, you know the position of the electron in the first shell, second shell, and third shell, and you also know the velocity, which is not possible. You cannot measure both of them at the same time accurately. So this was the second drawback. After that, after Heisenberg's uncertainty principle, the wave model of atom became quite prevalent. People, they were of the opinion that electron has got a wave nature. Based on that, a scientist, Schrodinger, he was very accurately, he was a mathematician. Schrodinger gave an equation. So a Schrodinger equation we have. This equation is actually h cap psi is equal to E psi. Well, as far Schrodinger's equation is concerned, this is a combination of wave equation and de Broglie's uncertainty, de Broglie's concept of duality. In some other video, I'll derive this equation for you. I'll tell you some extra about Schrodinger's equation, and I'll name that video as Schrodinger's equation. We'll see different form of Schrodinger's equation. I'll derive it for you. But for now, you should understand that it is h cap psi, which is equal to E psi. Now, what is psi? Psi in this case is a wave function. Wave function. What is wave function? Wave function again is an amplitude, but all values of amplitude are not wave function. To work as a wave function, the value of amplitude has to be orthonormal. Orthogonality and normality has to be followed by that value. Here in this case, I will not go into the details of that. In some other video, I'll give you the detail of all that, because I'll be making some videos for quantum chemistry also. In that, I'll explain it to you. Here you'll see h cap. This is the Hamiltonian coefficient. This is Hamiltonian coefficient. A coefficient is a value which, when multiplied with a operator, gives you a particular property of an electron. Like Hamiltonian coefficient, when it is multiplied by an operator, that is I, it will give you the energy of the electron. So what Schrodinger did, he used this equation and calculate the energy of the electron in the first shell of hydrogen, and very accurately it was nearly 2.18 into 10 to the power minus 18 joules, as it was calculated by Bohr. So that gave an evidence that electron, it has got a dual character, because according to Bohr, he was considering electron as a particle, and he calculated the energy this for electron in the first shell of hydrogen. Using wave equation, Schrodinger also calculated the same value of energy for electron. So we have different coefficient, like with Hamiltonian coefficient, if you are multiplying it, you are getting energy. With Laplacian, you will get another value. With Hermitian, you will get another value. That all I'm going to explain to you later on. But for now, this is Schrodinger equation. So by now we have a wave mechanical model of an atom. So if we see what wave mechanical model is, wave mechanical model. Well, in nutshell, we can say that according to wave mechanical model, an atom consists of centrally placed nucleus that contains neutrons and protons, and circular path around the nucleus in which you will get negative charge, and the negative charge is always in the form of waves. So in the first shell, you can see a wave of negative charge moving like this, somewhat like this. So if you will see the second shell, in second shell, the wave will be somewhat like this. You'll see one thing, you'll observe that the amplitude in the first shell, say I'm representing it with xi1, this for the first shell, is lesser than xi2, which is in the second shell. So xi1 is larger than xi2, which is larger than xi3, and so on. So as you move away from the nucleus, the amplitude of this electronic wave decreases. Now the question comes to our mind, what value or what information this amplitude gives us? Well, the amplitude of all the waves have got a property associated with them. Like when we talk about sound wave, the loudness of sound is related to the amplitude of the wave. The larger the amplitude of the wave, the more louder will be the sound. Likewise, for light wave, if we say the intensity of the light is related to its amplitude, the larger the amplitude, the more intense the light will be. Then what physical significance xi has got in this case? Xi1 has got a larger value, xi2 has got a lesser value, and as you move away from the nucleus, the value of xi decreases. Well, in this case, I want to tell you one thing, that xi itself does not have any physical significance. So xi, no physical significance. There's no physical significance of xi. It is actually xi square which has got a physical significance. Xi square gives us the probability of finding an electron in a given volume. So what you can see that xi1 has got a higher value. The value of xi in the first shell is larger. That means the value of xi square is also larger. That means the probability of finding an electron is higher in the first shell. It is lesser in the second shell. It is still lesser in the third shell. So as you are moving away from the nucleus, the value of xi is decreasing. So the value of xi square is also decreasing. And as a result of that, the probability of finding an electron is also decreasing as you are moving away from the nucleus. So this is what a physical significance xi has got associated with itself. Dear students, we'll move ahead. According to wave mechanical model, we'll see what are shells. Well, as far as shells are concerned, I can say that shells are nothing but a simple three-dimensional region around the nucleus. It is a three-dimensional region around the nucleus where the probability of finding an electron is finite, where you can get an electron. So if you want to write it down, you can write it down, the definition of shell, because it can be asked in your exam. What is a shell? A shell is a three-dimensional space around the nucleus where the probability of finding an electron is finite, where you can get electron. Now, the other thing, that is, what is a subshell? Subshell. Again, a subshell is a three-dimensional space within the shell where the probability of finding an electron is maximum. So a shell is a three-dimensional space around the nucleus where you can have that negative charge. Electron, see, by no means here electron means a particle. I'm not saying that electron is a particle. It's a negative charge. So around the nucleus, the three-dimensional space where you can get that negative charge is known as, where you will have finite probability of finding that negative charge, is a shell. The space within the shell where the probability of finding that negative charge is maximum is a subshell. Now the next question comes to our mind, what is an orbital? This is something on which you have to pay attention. Orbital. It is the three-dimension orientation of electrons around the nucleus. Three-dimensional orientation of electrons around the nucleus, that is known as orbital. So according to wave mechanical model, like Bohr's model, we have S subshell, we have P subshell, we have D subshell, and we have F subshell. Now, if these are the subshells we have, then then what are the orbitals? Orbitals refers to the three-dimensional arrangement of their electrons. We have one orbital in S subshell, we have three orbital in P subshell, and we have five orbitals in D subshell. Again the question comes, what does that means? Do these orbitals accommodate electron like they were doing in the case of Bohr's? No, because according to Bohr's model, every orbital can accommodate two electrons, and according to him, electrons are particle, whereas in this case, electron is simply a negative wave. So we'll see. This means the electron of S subshell can orient only in one way around the nucleus. I'm drawing these coordinates, that is X, Y, and Z. So the electrons can orient themselves now. Suppose I'm talking about S subshell. S subshell, the electron of S subshell, they are evenly distributed in a spherical manner. So S subshell appears somewhat like this. It is roughly spherical. Around the nucleus, it is roughly spherical. So this is how the S subshell will appear. It has got a spherical cloud around the nucleus. Next we'll talk about P subshell. So let us see P subshell. Well, P subshell has got a dumbbelled shape. It has got a shape like this. So you can have this dumbbell. Now suppose here I have X and Y axis. Again X and Y axis, again X and Y axis, and along with that I have got a Z axis also. This time I am drawing Z axis because I will show that to you also. Now they are doubled, and if the electronic cloud, if that dumbbell shaped electronic cloud is on X axis, it can be on X axis like this. It can also be on Y axis like this. It can be on Z axis also. Like this. That charge can be on Z axis also. So P subshell itself is dumbbelled shaped electronic cloud. It's like this, dumbbell shaped electronic cloud. That electronic cloud can be on X axis, Y axis, and Z axis. Collectively it is also forming some sort of a spherical field. So the dumbbell which is on the X axis, we call it Px. The one which is on the Y axis, we call it Py, and the one on the Z axis, we call it Pz. So according to wave mechanical model, shells are the three-dimensional space where the probability of finding an electron is finite. Subshells are the three-dimensional space within the shell where the probability of finding an electron is maximum. And orbitals are the three-dimensional orientations of electron. As the electron of S subshell can orient in spherical form, that of P subshell can orient itself in dumbbell form, and that dumbbell can be on X axis, Y axis, and Z axis. That electronic field, we cannot say 2 electron or 3 electron or 4 electron, because according to this model, electrons, they are not particle, they are wave. So that negative charge is on either x-axis, y-axis or z-axis. So this is how p subshell it appears. Next we'll see d subshell. Well, in here also, in case of d subshell, we have 5 orbitals. And d subshell, as far d is concerned, that is also made up of dumbbells, but we have 2 dumbbells. So it is doubled. First I'll draw the axis for you. Suppose x, y. Here in this case, y, z, z and x. Likewise, x and y. It can be anyone, either x or y, but this one is a z1. This is a z1. So we'll see how this double form it exists. I said that D will have 2 doubles, and those 2 doubles can be either between the axes, like here you have one double, you can see like this, another double can be like this. So here you got an electronic field where you have 2 doubles. Likewise, in YZ plane also, in this plane also you have got 2 doubles. One is this, and another one is like this. So here you have 2 doubles. Here also you'll have 2 doubles. So the first one is dxy because it is in xy plane. The second one is dyz because it is in yz plane. The third one is dzx because it is in zx plane. So out of 5 orientation, 3 orientations can be in such a way that they are in the interaxial plane, in between x and y plane and y and z plane, z and x plane. The 2 other orientations can be directly on the axes, like on xy axis, so here you have these orbitals directly on the x and y axis. The other form is where the orientation will be like this, in such a way that both the orbitals they are on the z-axis. If both the orbitals they are on the z-axis and they are overlapping with each other, see here what is happening, both the orbitals they are overlapping with each other. Whenever charge it overlaps, whenever the orbitals they overlap sideways, they form pi electrons. So here you will have a ring of pi electrons. A ring of pi electrons in YZ plane, in X or YZ plane. So this is how the 5 orbitals of d subshell they are oriented. As far they are concerned, the orbitals, or we can say the electron of d subshell can orient in 5 type. It is doubled, so it can orient in xy. So here I have dxy. Here I have dyz, here I have dzx, here I have dx square y square, and here I have dz square. So the electron of d subshell can orient themselves in 3-dimensional space in 5 different ways. Dear students, here I would like to add one more thing, that these 3 orbitals, they behave in one way because they are in interaxial plane. And these two orbitals, they behave in a different way because they are directly on axes. The first three orbitals, they are in the interaxial plane, so their behavior is similar. And we call them T2G orbitals. Whereas these two orbitals, they behave in a different way because they are directly on the axis. We call them EG orbital. See, you people are not going to use these notifications or these notations EG and T2G in 11th standard, but definitely you are going to use them in 12th standard. So it is better to make a base and better to understand them on time. So D subshell has got a double form. The electron can orient in 5 different ways where they can directly orient on the axis like x square, y square and z square. Those are EG orbitals. Or they can orient between the axial planes like between x and y and z and zx. Those are known as T2G orbitals. So this is what the shape of D subshell is. Next, I would like to tell you nodal plane. Nodal plane. Well, if we talk about a wave, suppose a wave is moving like this. We do have certain places where the value of wave is 0. Here you have crust, here you have trough. The crust is the part of the wave, the trough again is a part of wave. But what about this part which I have marked? This is not part of a wave because here the wave character is 0. So the three-dimensional space, three-dimensional So the three-dimensional space around the nucleus, where the probability of finding an electron is almost 0, is known as a nodal plane. So again, what is a nodal plane? It is the 3D space around the nucleus where the probability of finding an electron is almost 0. Never say 0 because there is the probability of finding an electron can never be 0. It is such a small negative charge which you can find anywhere. So it is the three-dimensional space around the nucleus where the probability of finding an electron is almost 0. Total number of nodal planes. Total number of nodes can be calculated by n minus 1. That means first shell will have no node, whereas the second shell will have one node. The third shell will have two nodes. So this is how we calculate total number of nodes. The nodes, the total number of nodes, they are made up of radial nodes and angular nodes. Radial node means what? It basically deals with the S subshell because it is spherical. So a sphere has got a radial probability. You move according to the radii, depending on the radii, you move in any direction. In a sphere, you move in any direction. The probability of finding an electron will vary in the same manner. That means you have got a radial probability. And when you got a radial probability, you'll have a radial node. That node, if it will come on the x-axis on a particular distance, definitely it is going to come on the z-axis also. It is going to come on the y-axis also at the same distance because you have got a spherical shattering or spherically shattered electron. These spherically scattered electron, they'll have the same node at the same distance on any of the axes, x, y, or z axis. So this is what a nodal plane is. A nodal plane is a three-dimensional region around the nucleus where the probability of finding electron is almost 0. In S subshell, you have radial node. How to calculate radial node? Well, number of radial nodes is always n minus L minus 1. So this is how you can calculate radial nodes. Total number of nodes, you know n minus 1. Radial nodes, you know n minus L minus 1. If you minus n minus L minus 1 from n minus 1, you'll get angular node. So they are generally equal to L. So this is how you can calculate radial nodes and angular nodes. And this is all about the nodal plane. And this is all about the wave mechanical model, in fact. Well, student, till here we have done the wave mechanical model, but while doing this chapter, we skipped a topic that is photoelectric effect. So photoelectric effect is what we are going to do now. I'll tell you what photoelectric effect is. Some of the formulas which you have already done will help you in understanding photoelectric effect. So we'll see photoelectric effect. Suppose in an atom here I have nucleus and this is the valence shell and I have got an electron in the valence shell. Since electron is negatively charged and nucleus is positive, there is a force of attraction from nucleus onto the valence electron. Nucleus is positive, it will attract its electron toward itself, it will also attract the valence electron toward itself. This force of attraction from the nucleus on the valence electron is known as work function. We call it work function. Well, we have certain atoms in the periodic table which are very large. Like I talk about potassium, rubidium, cesium. Rubidium and cesium, they are, means cesium, I can say that it is the largest atom. Francium is radioactive, so we will not include it. So rubidium, cesium, which are larger in radii, the largest and the second largest atom, they have very large atomic radii, such a large atomic radii that in their case the work function is very less. And the work function is so less that even when a photon, here I have got a photon, even when a photon of a particular wavelength strike on this electron, it provides sufficient energy that the electron will move out. Suppose the energy of this photon, I am marking it with ER, that is energy of radiation. So whenever a photon, see, cesium and rubidium has got such a larger atomic radii that the work function in them is very less. So even when a photon will strike on the electron, it will take out the outer bound electron, the valence electron, which has got the minimum work function on it. So that electron will move out. This is known as photoelectric effect. Photo means photon, electric means motion of electrons. So a photon is striking, it is taking out an electron from an atom. This is photoelectric effect. Dear students, if you want to observe a photoelectric effect for a photoelectric effect, the energy of radiation has to be greater than or equal to work function. Suppose the nucleus is attracting the valence electron by an energy of 10 kilojoule and the radiation which is striking on the electron is of 9 kilojoule. That radiation is not having sufficient energy to take out that electron, so no photoelectric effect will be observed. Suppose the radiation has got an energy of 11 kilojoule. So when a radiation of 11 kilojoule is going to strike on the outer bound electron, with 10 kilojoule it will take out that electron and 1 kilojoule will become the kinetic energy of the electron with which it will move. Because you know very well, energy can neither be created nor can be destroyed. So if a photon of 11 kilojoule is striking on an outer bound electron, it will provide 10 kilojoule to take out that electron and remaining 1 kilojoule will become the kinetic energy of the electron. So that means that if you want to observe photoelectric effect, the energy of the radiation has to be equal to or greater than work function. We'll see both the cases. Suppose if energy of radiation is more than work function, this is same which example I gave you, then in that case the energy of radiation is partially used to overcome the work function and it is partially used as kinetic energy of the electron. So if a radiation of 11 kilojoule is striking on the electron, the kinetic energy of the electron will be 1 in the same example. And in the same example, if the work function is 10 kilojoule and a photon of 15 kilojoule is striking, then what will be the kinetic energy of the outer moving electron? That will be 5 kilojoule. Because with 10 kilojoule, it is taking out that electron and rest 5 kilojoule is becoming the kinetic energy of the electron. So this is what photoelectric effect is all about. Dear students, it may happen, here in this case, see what I have taken an example where the energy of radiation is more than work function. It can happen if energy of radiation is just equal to work function. Well, if energy of radiation is just equal to work function, then in that case, then kinetic energy of outer moving electron is 0. 10 kilojoule is the work function and 10 kilojoule is the energy of the radiation. So when the radiation is striking on the electron, it is providing sufficient energy for the electron to just leave its shell. And we consider that the kinetic energy is 0. So in that case, kinetic energy is 0. And such a radiation, see, if energy of radiation is just equal to work function, we mark it as ER0 and we call it threshold energy. Threshold, you know, barrier. Work function was 10 kilojoule. So what is the barrier for a photon to take out that electron? That is 10 kilojoule. If the energy is less than 10 kilojoule, no photoelectric effect. On 10 kilojoule, photoelectric effect will be there, but kinetic energy will be 0. More than 10 kilojoule, there will be a photoelectric effect plus kinetic energy. So barrier is 10 kilojoule. So that is the threshold energy. So what I can do, I can, you can see this formula. I can use this analogy over here in this formula. In that case, my formula will become energy of radiation is equal to ER0 plus kinetic energy of electron. So this is what I'll get. You know, energy of radiation is equal to h nu. So here in this case, I can also write h nu is equal to h nu naught plus kinetic energy of electron. This, what is this nu naught? Nu naught is threshold frequency. So this is threshold frequency. So this is threshold frequency. What we can say, if the value of frequency is less than nu naught, you know that E equal to h nu, where h is 6.63 into 10 to the power minus 34. That means the value of h is constant. That means the energy depends only on frequency. So nu naught is the threshold frequency. It is the frequency below which if you got a frequency, there is no photoelectric effect. At this frequency, there is a photoelectric effect, but the kinetic energy is 0. And beyond this, if you got a frequency, not only photoelectric effect, but you will also have some kinetic energy associated with the photoelectron. So from here, I can also write kinetic energy of electron is equal to h nu minus nu naught. This is the other formula I have got. H is constant. So kinetic energy of electron is h nu minus h nu naught, where h is constant. You know one more thing, that C is equal to nu lambda. So nu is equal to C by lambda. If I put this relation in this formula, I will get kinetic energy of electron is equal to h C by lambda minus C by lambda naught. Where lambda naught, you had threshold frequency. So lambda naught is what? Threshold wavelength. C is common. So kinetic energy of electron is equal to h into C 1 upon lambda minus 1 upon lambda naught. So many a time you will get questions based on this. Like a question will be given to you, the threshold wavelength for a particular atom X is this. A radiation of this wavelength is striking on that atom. What will be the kinetic energy of the electron which is moving out? Likewise, they can say that the work function is this. A photon of this frequency or this wavelength is striking. What will be the kinetic energy of the ejected electron? So you know the work function. Since you know wavelength and frequency, from wavelength or frequency, you can easily calculate energy of radiation. These are the formula which I taught you in the first lecture. So you'll get the energy of the photon. From energy of the photon, you will subtract work function, you will get kinetic energy. So these are the formulas which you are going to use in photoelectric effect, and this is all about photoelectric effect. With this, we have finished up with our chapter, that is structure of atom. Next chapter after this we'll be doing chemical bonding. Again, student, I want you to go through all these lectures and kindly keep on revising them. The more you will revise them, the more comfortable you will get in understanding them. And in case you got any doubt anywhere, any problem you have, you can message me on my number. And please, the people who have not subscribed my channel till now, I'm asking them to please subscribe my channel so that you'll get all notifications at time and you'll get all the lectures on time. So please do subscribe. Thank you very much.